I welcome you all in this NPTEL online certification course on mechatronics. Today we are going to talk about a very important component, analog to digital converters. Many of the sensors which we are using in a mechatronic system, they give the analog output, and the microprocessor or microcontroller which are going to process these signals, they require the digital input. So, is the need of analog to digital converter. Okay. So, in this lecture I am going to talk about this. I hope you will enjoy that. So, here we are at this phase, input signal conditioning and interfacing, and here I am going to talk about this analog to digital converter. So, see how does the analog signal looks like. So, the analog signals are actually continuous signal, and this is how they look like actually. Okay. Whereas, the digital signals are basically they look like this, they are either on or off. Okay. So, most of these digital signals have got only two states, as I said, on and off or high and low. A system using two state signal allows the application of very powerful logic, very powerful tool called Boolean logic and binary number representation. So, I will be talking about these also in my upcoming lectures. So, let us talk a little about the digital signal. As I said, the output from most sensors tends to be analog form, and the size of output being related to the size of input some way or the other. And as I said, a microprocessor is used as a part of measurement or control system, and it can take only the digital signal. Okay. So, these sensor signal need to convert it into the digital form before they can be used by or they can be processed by the microprocessor. Likewise, most actuators operate with analog input. Okay. So, for that we require the conversion from digital to analog, and that I am going to talk in my next lecture, the analog to digital digital to analog conversion. Okay. So, the digital output from microprocessor has to be converted to analog form before it can be used by actuator, as I said, and I am going to talk about this component, that is digital to analog converter, in my next lecture, so that the signal can be used by the actuator. And here as you see we have the microprocessor. Okay. And I need the signal for microprocessor to be a digital signal. Okay. So, since the most of the sensors are analog sensors, I need one analog to digital converter over here, so that the signal can be processed by the microprocessor. As I said, the beautiful thing with the binary with the digital signal is that we can use the binary or Boolean logic basically, okay, in signal processing. Okay. So, before we proceed, let us have a little about the binary system, so that we have some understanding about it before we proceed further. So, the binary system is based on two symbols or states, that is what we call 0 and 1, and these possibly say 0 may corresponds to a say 0 volt and 1 may corresponds to the 5 volt. Okay. And these 0 and 1 are termed as binary digits or bits. Digit position in a number indicates the weight attached to each digit. At in a number, in a binary number, okay, the digit position in number is indicated by how much weight is attached to that. Okay. And weight is increases by a factor 2 as we proceed from right to left. Okay. So, this is like this, say bit 0 is represented by 2 to the power 0, bit 1 is 2 to the power 1, bit 2 is 2 to the power 2 and bit 3 is 2 to the power 3 and so on. Okay. So, let us take an example, say number 15. Okay. So, this number 15 can be represented by say or rather I can write the 15 as 2 to the power 3 which is nothing but 8, 2 to the power 2 which is 4 and 2 to the power 1 which is 2 and 2 to the power 0 which is 1. So, 8, 4, 12, 13, 14 and 15. So, this gives me the 15. Now, here all these are present. Okay. So, we represent the presence of all these by number 1. So, you have 1 here, 1 here, 1 here, 1 here. So, this is the binary representation of 15, that is 1 1 1 1, and the combination of bit is represents actually the words. So, for 1 1 1 1 is a 4 bit word and this 4 bit word basically represents a number 15 in the decimal system which as we have seen. So, such a word could be used to represent the size of a signal. Okay. And to have little bigger unit, 1 byte is taken equal to 8 bits. So, this table actually indicates the decimal and their binary equivalents. So, basically as I have just talked about 1 1 1 is equal to 15 and so in binary if I am writing say 0 0 0 here, that is my all are absent basically. Okay. So, this is actually 0, 0 0 1 is equal to 1. So, actually this is basically what 2 to the power 0. Okay. And this is basically what, this is equal to 2 to the power 1, that is present. So, this is 2 and this is actually what 2 to the power 0 plus 2 to the power 1. So, both these are present. So, this is equal to 3 and here this is basically what 2 to the power 2. So, this is 4 and this is 2 to the power 2 plus 0 plus this is present. So, this is 2 to the power 0. So, you have 5. So, likewise. Okay. So, likewise we can establish a that is we can have a binary representation of a decimal number in a 4 bit representation like this. Now, let us look further on analog and digital signal. Okay. So, analog to digital conversion involves converting analog signal into basically a digital signal, and digital signal we know that it is nothing in the form of binary words basically. So, a clock supplies regular time signal pulses to the analog to digital converter, and every time it receives a pulse it samples the analog signal. Okay. So, this analog to digital converter basically needs a sample and hold circuit basically. okay, for the sampling purpose. Okay. So, you have the input side, you have an analog signal, there is a sample and hold circuit, okay, for sampling and holding of it, and then this is given to analog to digital converter, and you get the output as the digital signal. Okay. So, this is how it is done. So, suppose this is my analog signal, as you can see over here. Okay. So, I have plotted analog signal versus time, and this is my clock signal. So, I am putting my clock at these point as this time basically. Okay. So, at this time if I am clicking my clock, so this value is being picked up over here, okay, and at 0 this value is being picked up, okay, and here this value is being picked up. Likewise, I am picking up the values, okay, and at this time I am putting up a clock. So, this value is being picked up like this. Now, you see, so this is the sampled signal, and if I talk about sample and hold, so this signal is held till the next clock comes basically, okay, next ticking comes. So, this signal is hold up to here, and then at this time interval, okay, another value will be held, okay, and it will be this value basically, okay. So, this value is held up to this duration, and then here it comes to 0. So, the 0 will be held, and then it will be coming over here, the same 0 is held up to here, and until unless this is held. So, this way this signal is being sampled and hold the analog signal. Okay. So, as a result of the sampling, basically we get this one, okay, and this sample and hold unit is necessary because analog to digital conversion requires a finite amount of time, that is conversion time, to convert the analog signal into a digital signal. Okay. So, looking at analog to digital conversion, as I said, analog to digital converter is basically an electronic device that converts analog voltage into a digital code. The output of the A to D converter can be directly interfaced to the digital devices such as microcontroller and computers. Okay. And analog to digital conversion conceptually involves two steps basically, what we call it as the quantizing and coding. Okay. So, that is first you have to quantize the signal, and then you have to give a code to that particular quantized value. Okay. So, the quantizing and the coding, this involves in conversion of analog signal into a digital signal. So, what is quantizing basically? This quantizing is the transformation of a continuous analog input into a set of discrete output states, okay, and coding is the assignment of a digital code for that particular quantized value, okay, word number to each output state. Okay. And the resolution of an analog to digital converter is basically is the number of bits used to digitally approximate the analog value of the input. So, the analog value of input you are being representing by how many bits, that basically tells you the resolution of the analog to digital converter. Okay. So, the number of possible states is equal to the number of bits combination that can be output from the converter. Okay. So, if there is n number of bits, then your number of states are going to be equal to 2 to the power n. Okay. Or say in case of a 3-bit device, it is going to be 2 to the power 3, or that is 8 output states. Okay. And the output states are usually numbered consecutively from 0 to n minus 1. okay, and that is in this case 0 to 7. All right, and total we are going to have 8 states basically. Okay. So, most analog to digital converters use either 8, 10 or 12 bit devices that resolves 2 to the power 8, 2 to power 10, 2 to the power 12 or 256, 1024 or 4096 states. Then the analog quantization size, this is sometimes called the code width, and this is defined as the full scale range of the AD converter divided by the number of output states. Okay. So, it is V max minus V min divided by n, where n is the number of the output states. It is a measure of the analog change that can be resolved by the converter. Okay. So, the number of analog decision points that occur in the process of quantization is n minus 1, okay, that is 7 in case of 3 bit device. Okay. Consider let us take a 3 bit device which has got 2 to the power 3 or 8 output states as listed. I am going to illustrate that. So, the output states are can be numbered from 0 to n minus 1, and the corresponding code word for each output state is listed as I am going to show in the next slide, and these are going to be the decision points basically, and so the code width will be V max minus V min divided by n, that is 10 minus 0 divided by 8. So, this is around 1.25 volt. Okay. And this means that the amplitude of the digitized signal that has an error of at the most 1.25 volts. Okay. So, the AD converter can only resolve a voltage to within 1.25 volt of the next analog voltage. So, here so, this 10 volt range 0 to 10 divided by 8 basically gives us 1.25. Okay. So, this is 0 to 1.25, 1.25 to 25. So, these are basically we are going to have, okay, and output states are going to be here. This is actually your capital N which I was talking to you 0, 1, 2, 3, 4, 5, 6, 7, 8, and these are the numbers basically means 0 to 1.25 volts, say I am representing by a binary number 0, 0, 0. Okay, and 1.25 to 2.5 volt I am representing by binary number 0, 0, 1. 2.5 to 3.7 volt I am representing by binary number 0, 1, 0. Okay. So, this is how this signal, analog signal is represented by the digital signal. Okay. So, a particular voltage range values are given a particular binary representation after the quantization. So, the question arises that if we are sampling your analog signal, what should be our frequency of sampling, and that criteria has been given by the Shannon. Okay. So, Shannon sampling theorem it basically helps us, or rather gives a guideline that how frequent we should sample our analog signal when we are going to represent it digitally. Okay. So, the first step for analog to digital conversion is to numerically evaluate the signal at discrete instant in time, and this process is what is called as sampling. Okay. And the result is a digitized signal composed of discrete value corresponding to each sample. Now, how fast or how often the signal should be sampled to obtain an accurate representation, because it is a very important factor, because if yours it needs a high speed hardware and large computer memory naturally, if you are going to do the sampling very often. Okay. So, the Shannon sampling theorem states that the sampling rate of the signal should be more than 2 times, okay, more than 2 times the maximum frequency component in the signal. So, whatever maximum frequency component is there in the signal, you have to sample it more than 2 times of that, okay, in order to retain all frequency components. Okay. So, Fs has to be more than 2 times of the maximum frequency component. Okay. So, where max, or what we is also called as Nyquist frequency, is the highest frequency component in the input analog signal, and the time period between so digital sample we could just evaluate by putting it 1 by Fs. Okay. So, if the sampling rate is actually 5000 hertz, what does this means? This means that the time interval between samples would be 1 by 5000, that is 0.2 millisecond. So, you have to do this sampling of your analog signal at the interval of 0.2 millisecond. Then let us look at a phenomena called aliasing. Okay. If a signal is sampled at less than 2 times its maximum frequency component, then aliasing will occur. Okay. So, say 12 equally spaced samples are taken over say 10 cycles of the original signal. Therefore, the sampling frequency is around 1.2 f0, where f0 is the frequency of the say original sine wave, and because the sampling frequency is is not greater than 2 times of f0, it will not capture the frequency in the original signal. Okay. So, the apparent frequency in the sampled signal is 0.2 f0, okay, that is okay, that is going to be there, or the 2 alias signal cycle for 10 original signal cycles it is there. Okay. And because of this, undersampling not only result in error, but also create information that is not really there. Okay. So, here you can see in this figure you have the sample points over here, okay, and you have the original signal and you have the alias signal. So, this signal which you have got by sampling, this sampling, this is the alias signal. Then to properly do the analog to digital conversion, okay, that is to properly acquire an analog voltage signal for digital processing, the following components must be properly selected and applied in this sequence. So, for example, the sensor is there which gives an analog signal. You need a buffer amplifier in order to amplify that signal. Then you need a low pass filter, okay, so for there, and then you need a sample and hold device, and once you have the sample and hold device, then you need an A to D converter for that, and then of course this can go to the computer memory like this, okay, and this way you can convert this your analog signal into the digital signal like this. So, the buffer amplifier actually isolates the output from the input and provides a signal in a range close but not exceeding the full input voltage range of the A to D converter, and the low pass filter removes any undesirable high frequency components in the signal that could produce aliasing, okay, because if you have a high frequency component and if your sampling frequency is less than 2 times of that high frequency component, you are going to get the aliasing. Okay. So, the cutoff frequency of the low pass filter should be no greater than half the sampling rate. The sample and hold amplifier maintains a fixed input value, okay, during the short conversion time of the analog to digital converter, and the converter should have a resolution and analog quantization size approximate to the system and signal, okay, and the computer must be properly interfaced to the A to D converter system to store and process the data. The A to D system component described can be found packaged in a variety of commercial products called data acquisition, okay, DAC or DAQ cards or module, okay, and these DAC products are available in a variety of form factors including PC and instrument panel plug-in card, a laptop computer, PC MCIA cards and standalone external units with standard interfaces, that is USB. Alright, DAC and modules usually support various high level language interfaces also, that is either C++ or Visual Basic, Fortran, that gives easy access to the product features. So, these are the commercially available product from the National Instrument LabVIEW software. National Instrument are there, and various forms of data acquisition products from the National Instruments, as you can see over here. Now, this analog to digital conversion, what are the methods and how this is done basically. Okay. So, let us try to understand this. The input to ADC is an analog signal and output is binary word, and that represents the level of the input signal we have already seen by quantizing and coding, and this A to D converters are designed based on the different principles, okay, such as successive approximation, flash or parallel encoding, single slope and dual slope integration, switched capacitor and delta sigma. Okay. So, I am going to talk about the first method, that is the successive approximation. Okay. So, in this case of a successive approximation, basically what is done is that you have a analog input being supplied to a comparator, there is a clock over here and there is a gate, and this gate basically I will be talking about this gate, the details of this gate in my coming lectures. Okay. So, this basically controls the admission of pulses to the storage register, and here is your say 4-bit storage register. Okay. And there is a digital to analog converter, this is being used, and again as I said I will be talking about digital to analog converter in my next lecture. Okay. So, in a analog to digital converter, a digital to analog converter is being used, okay, in this method of successive approximation, and from here we get the digital output. Okay. So, how the process takes place basically, this is illustrated over here, how this conversion from analog to digital takes place. So, a voltage is generated by the by a clock emitting a regular sequence of pulses which are counted in a binary manner, and the resulting binary word is converted into an analog of voltage by digital to analog converter basically. Okay. And this voltage rises in steps and is compared with the analog input voltage from the sensor. And when the clock generated voltage passes the input analog voltage, the pulses from clocks are stopped, okay, being counted by a gate. And the output of the counter at that time is basically the digital representation of the voltage. Okay. And when the comparison could be while the comparison could be accomplished by starting the count at 1, the least significant bit, and the processing bit by bit upwards, a faster method as I said is by this method, that is the successive approximation. Okay. And this involves selecting the most significant bit that is less than the analog value, and then adding successive lesser bits for which the total does not exceeds the analog value. For example, we might start the comparison with say 1 0 0 0, okay, this byte, okay, and that is with these 4 bits. If this is too large, we try with then 0 0 1 0 0, and if this is too small, then we try with 0 1 1 0. So, okay, and if this is too large, we again try with a different number. Now, because each of the bits in the word is tried in sequence with a n bit word, it only takes n step to make the comparison. Okay. So, thus in this successive approximation, basically what is there, you have an analog signal, you sample that analog signal, okay, and give a representation to a digital representation to that analog signal, okay, sampled analog signal, and you check basically and that digital representation is basically converted into an analog for comparison purpose with the actual analog, okay. And when the comparison is there and the deviation is not found, then whatever the digital value has been there, that digital value is actually taken as the analog digital representation of the analog signal. Okay. So, this is how this successive approximation actually works. Okay. I will again explain you. So, you have a clock, you sample it, okay, and after sampling give a digital representation to that, okay, and this digital representation is also available in the form of output. But whether this output has to be taken or not taken, or this is correct or not, to check that, we take this digital signal and use a digital to analog converter and compare it with the analog input. Okay. And we have I have already explained in my previous lecture about the comparator. Okay. So, if where this converted your analog signal and the actual analog signal, if they are comparing, okay, then this particular value of the bit or signal, digital signal is selected or taken as the analog, that is the taken as the digital representation of this analog signal. So, this way you have the digital value of that. Okay. So, if the clock has frequency f, then the time between pulses is naturally going to be 1 by f. So, hence the time taken to generate the word, that is the conversion time, is going to be n times of f, where n is the step to make the comparison. So, these are the further references which you would like to go through for further reading. Thank you very much.